Okay, from yesterday we had left off with briefly introducing the ideal gas law. So here we have that equation right here, and when we're solving these problems, what makes things a lot easier, okay, is when we're actually comparing that to standard temperature and pressure. Because when you do that, of course, we know what a lot of these variables are. Notice how short these problems are essentially worded, because when you get to what was handed out as worksheet 2, you're given a lot more information. In other words, when it comes to an ideal gas, sometimes you're given not just the volume, but you might be given the temperature and possibly a different type of pressure, because not all gases are going to be measured at STP or near STP or raising them to standard temperature and pressure. But as we had discussed yesterday, okay, when we're doing these, the pressure needs to be in atmospheres, the volume should be in liters, and here is your number of moles. So that's, you could say moles, which is how you go from grams to moles or moles to grams. This is a constant, and then this is 273 degrees Kelvin. So we got this R constant that we had mentioned was this, which is 0.0, oh shoot. I was going to write 8, but that was a little too early, 0.0821, okay? So where that number comes from is when we're dealing with the ideal gas law. Notice when we say atmospheres, it's going to be at 1 atmosphere of pressure. And we have 22.4 liters, okay? And it's just a conversion unit. Don't get 22.4 mixed up with this, because that will be something that we use when we get to gas stoichiometry. But this constant, 0.0821, is just as you would guess. We know what this value is for every 1 mole, and we have 1 atmosphere pressure. If we have 22.4 liters, no coincidence, you take 22.4, and we divide that by what's left on the right-hand side, 273, and then what happens, that's where we get this constant of 0.0821. And that's what you can do when gases are measured at STP. Okay, so we're just going to do a couple of examples here, and then we'll get you on your way. All right. So it says, what is the mass of carbon dioxide when 855 milliliters expands due to possibly an increase in temperature? And we're not concerned about where it started, but we're increasing this temperature to standard temperature and pressure. Okay, so what that would mean then is, as we start this, we know the pressure, 1 atmosphere. Okay, the volume, well, what is the mass of carbon dioxide, which means we have to fill in the rest of our variables, and we'll get to that. For some reason, I had confused myself again. I didn't, trying to process and be 2 steps ahead of myself, which is not happening. For some reason, I was thinking we had to count for that 22.4, but again, that is just a conversion factor. We're given that volume right here, but remember that has to be in liters. So if we are going from milliliters to get to liters, we need to divide that by 1,000. And notice if that had not happened, if you left this in this number here, 855 in milliliters, it's not going to change anything. You just have to just do what the question asks, and that would be divide by 1,000 eventually, because some of these problems that were handed out to you, what's the volume in milliliters? But we'll get to that in just a moment. So changing this to liters, dividing that by 1,000, we just move the decimal place 3 times. So 1, 2, 3, that's where our decimal is. So now we're in liters. Okay, so going right on down the line, we know what R is. That was that constant we're talking about, 0.0821. Okay, and then standard temperature, as we know, is 273 degrees Kelvin. The only thing that we do not have, of course, is this N variable, which we know is the number of moles of this gas. And of course, in this case, it is carbon dioxide. All right, so here is our unknown, carbon dioxide. Here is our unknown, which is our N value, which is moles. And once we calculate that in moles, it's just a quick step to get that into the mass of carbon dioxide in grams. So once we get it to this spot, we just do what the formula tells us to do. And since this is 1 atmosphere, we can just put this on the left-hand side of our equation, which is 0.085. 0.855, sorry, equals 273 times 0.0821, and we have our N variable. Okay, so one thing to keep in mind is when you're doing these, if when we get further down the road with this, and maybe some of you had figured this out, is that every time you have these variables next to each other, we're accommodating for that 22.4. So what you could essentially do is say 0.855 equals 22.4 N. And again, we had arrived to this because if we divide 22.4 by 273, we get 0.0821. So we are accounting for that, but this is just one of those aspects to maybe some of you had already figured that out, perhaps. But there's nothing wrong with doing this. We're still going to get you to the same spot. So the next thing we need to do is get N by itself. So of course, using your algebraic skills, 22.4, 22.4, we're going to get N equals, okay, and hopefully your batteries are low. Is that my calculator or my head? No, it must be my calculator. Okay, so depends who you ask. All right, so 0.855 divided by 22.4, and that gives us 0.038. So this content, we can get rid of some of this. We'll get rid of the volume. And we know that's going to be the same, and maybe we'll have this in another problem. So that gives us 0.038. Okay? So we get this down to 0.038. Now remember, that's in moles. That's not in grams or mass of carbon dioxide, but it's just one small step that we have to take, and that would be using your dimensional analysis of saying 0.038. Think of how you get from here to this mass of carbon dioxide. Okay, so again, this is moles of CO2. If you had said you're going to multiply by 28, that would be correct. Okay, and that number comes from this. To cancel out that mole of carbon dioxide, we need to put moles of CO2 on the bottom, and then that would give us our grams of CO2. Okay, every oxygen is 16. And I already goofed on that, didn't I? I said 28, okay? We got 16 times 2 is 32. 32 plus 12. We're going to put 44.01 grams of carbon dioxide there. So the moment we take 0.038 times 44.01, that gives us 1.67 grams of carbon dioxide. 1.67 grams of CO2. All right, so that's how we apply this ideal gas law. A lot of this is just, again, this is composition gas stoichiometry. We haven't gotten to the reaction side yet. Okay, I'm going to go ahead and hit pause, and we'll look at that paper that was assigned to you. Okay, so we'll just go ahead and look at number 8 on worksheet 1. That's the one that has says chemistry, molar gas volumes on top. Number 8 says, what is the volume in liters, okay, at STP for 8 grams of oxygen? Okay, so it's asking what is the volume. So some of these we're going to have to switch up a little bit. Notice in our last problem we were given the volume and we had to find our mass. So in this case, okay, here is our question mark. You'll probably notice, and maybe some of you that have that done already, we're either looking for that variable or that one. Because at STP, we know that these three are always going to be constant. 273 degrees Kelvin, 1 atmosphere pressure, and then 0.0821, so what you say, liters per degree Kelvin. And that's where this comes from. So we're given other variables. We had 8 grams of this, of oxygen. But notice grams and moles, that really does not coincide. It's not really, it's useful, but we have to take one initial step to get to moles, and that's going back to last August and September, which means if we have 8 grams of, don't do just that, or else you're going to be off by a factor of 2. Okay? So as you may have guessed, if you have 8 grams of O2, not just oxygen, we need to convert that to moles of O2, or oxygen. And then upon doing that, we've got 32 grams of oxygen, okay? And then approximately, okay, 8 goes into 32, I believe, 4 times. So if that's the case, that would be 0.24, 0.25 moles of O2, okay? So 8 over 32 would give you a quarter. So upon doing that, this 8 grams of oxygen then can be, that doesn't quite show up, does it? It's a little too high. Oh, okay, I guess it does. All right, 8 grams, we change that to 0.25 moles of oxygen. So now we got everything in place that we need. We just want to do what the formula tells us to do, which then is saying, you can just say your volume, okay? Because anything times 1 is just going to give you that variable or that number regardless, okay? And if you wanted to take a shortcut again, if you multiply these two, you're going to get 22.4, okay? So this is one way of looking at it. You can have 0.0821 times 273, and then we have times 0.25, okay? As we already established, we know if we're multiplying these two, a shortcut we can take, okay? Now, it's not always the case that you can do this, and maybe it's a good idea not to get used to this, but you can say 22.4 times, okay, 0.25, okay? You're getting the same thing. All you're doing is you're multiplying these, you're getting that constant of 22.4 back again. So 22.4 times 0.25, 22.4 times 0.25, that gives you approximately 5.60 liters. Volume equals 5.60 liters. So if this was asking for what was the volume in milliliters, again, you would just divide that by 1,000. Volume would equal 0.00560 milliliters. Okay, so hopefully you found that helpful, and tomorrow we'll discuss parts of worksheet 2. I don't think there's really any advantage of possibly working together. You can perhaps just put some of those variables in where some of these numbers go, and What I mean by that is, for instance, on that second paper where it says, what is the temperature of a 274 gram sample of methane confined in a 300 milliliter bulb at a pressure of 198.7 kilopascals, okay? So a couple of things you need to do. One, okay, is you need to convert 300 milliliters to liters, okay, which is pretty simple. We can certainly accommodate that. Which then means we've got 0.300 liters, okay? And then the R is always going to be the same, 0.0821, okay? And then it's asking for the temperature, so we don't know. It is a known substance, so we can take that 274, 0.274. Now that's grams of methane, CH4. Eventually you're going to divide that by, so you're 12 by 16 grams of CH4. That gives you a mole of CH4. So whatever answer you get here, okay, just put an X in a circle. That goes down here, okay? And then it's asking for the temperature, but it also says your pressure is 198.7 kPa, and we know you need to convert that by putting that in atmospheres, which is 101.325 kilopascals will get you that variable into atmospheres. Okay, so maybe some of you are working just a little bit ahead, so I thought maybe that you would find that helpful. So what you would find out is the answer for number 1 on your second paper is 421.43 degrees Kelvin. Okay, so that's all I have. Chances are we'll be discussing this more tomorrow. And if we're lucky, maybe we'll be back in session on Friday. If not, we'll just keep pushing forward. So that first paper, have that ready to go by Friday if we are in session. And then the second paper, the one that we just briefly got started with, let's have that ready to go by, I hate to say Monday, but because really I don't like assignments due on Mondays, but we really don't have a choice in this matter. Okay, so thanks for tuning in. Stay warm, stay safe, and we will catch up to you next time.